Welcome. Now, let us start looking at a totally different aspect or the next aspect. Earlier it was all in terms of getting the equations of state or considering different equations of state to improve the generality of application. As you know, the equation of state is something that relates the P, V and T of a pure substance. Now, we are going to use that information P, V and T to estimate the other thermodynamic properties, and the way we are going to do that is use something called residual properties. If you use this formulation, it becomes possible to estimate the other thermodynamic properties. Remember that U, S, H, A and G, we could estimate the other properties using PVT. So, let us take a look at how to go about doing that. The motivation, as we all know by now, is that U, S, H, A and G are not easily measurable. They are of course estimated, they can be estimated by the more easily measurable P, V and T, and we are going to limit ourselves to gases to begin with. Pay a little bit of attention to this. For any thermodynamic property, okay, for the 5 that we are looking at now, you can write this for any thermodynamic property or even combinations of thermodynamic properties. The actual value minus the ideal value, or the difference between the actual value and the ideal value, is actually called the residual value. Now, to give you an example, if V is the actual molar volume of a substance and V ideal gas Vig is the ideal gas molar volume, then the residual molar volume represented as Vr is given as the difference between the actual value V and the ideal value Vig. Let us take this a little further. This is the basic definition of a residual property now given in terms of molar volumes, and since this is the molar volume, let us try to take this a little further. This is nothing but V minus V ideal gas is RT by P, and we know that PV by RT is Z, and therefore, we can write this as PV by RT, and therefore, if you take this out, you are going to get RT by P into Z minus 1. Rather, we are writing V in terms of Z, which is ZRT by P, and therefore, RT by P common out Z minus 1. We will call this equation 324. And since we can write this for any thermodynamic property, we could of course we will give you a formal expression for that. If M is any extensive thermodynamic property such as U, S, H, A, G or V, the residual property of that M is nothing but M minus M ideal gas. We will call that equation 325. Now, let us kind of deviate slightly. It is still very related, but this becomes essential to develop a means of relating the excess properties to PVT. Therefore, let us kind of deviate slightly and consider the quantity G by RT. The residuals of this could also be written, as you would see. We will start considering G by RT. Please work out the dimensions of G by RT. If you need, you can go back to your notes, find out what the dimensions of G are, R are, T are, and then work out the dimensions. Take about 3 minutes to do it and convince yourself that it is dimensionless. Okay, you should have gotten no dimensions for G by RT. If not, please check after the class. Now, let us consider the derivative, the total derivative of J by R T. You know that this is this is of a u by v form. R of course is a constant, but G and T are variables, and it is of the u by v form, and therefore, the total derivative of J by R T is nothing but denominator function into derivative of the numerator function minus the numerator function into derivative of the denominator function divided by the denominator function squared. So, in other words, denominator function R T into derivative of the numerator function d g minus the numerator function g times the derivative of the denominator function R T divided by R T squared, which can of course be you take the common terms out, 1 by R T dg minus g by R T squared, one of the r's will get cancelled, g by R T squared times dt. Now, okay, we will call this equation 326. Now, let us express dg and g in terms of the expressions that we already know. In other words, we are going to use equation 2.8 for dg and 2.3 for g. You do not have to go back and check, you will these equations will come back to you when I substitute them. If you use these two equations in 326, dg by RT equals 1 by RT from here, dg is nothing but for a closed system minus STT plus VDP. So, that comes in here minus g by definition is H minus Ts. So, H minus Ts, that is equation 2.3 by RT squared dt, which can of course be simplified to V by RT dP minus H by RT squared dt. I am sure you can see this here. Equation 327. Now, this is the total differential. You know that total differential of an exact differential can be written as a partial differential times dou g by RT dou p dP minus or plus dou g by RT dou t dt. Therefore, this should be equal to, okay, let's take one step at a time. By considering g by RT as a function of p and t, we can write V by RT as dou g by RT dou p, this term at constant temperature here. We will call this equation 328, and H by RT equals minus t, because H by RT squared will turn out to be the partial derivative here with respect to temperature at constant pressure, and therefore, H by RT is minus t dou g by RT dou t at constant p. We will call this equation 329. By dividing equations 2.1 and 2.3 by RT, this will come back to you straight away. You don't need to go back. U was nothing but H minus PV, or H equals U plus PV. Therefore, U equals H minus PV, and you divide throughout by RT. U by RT is going to be H by RT minus PV by RT, equation 330, and S is S by R equals H by RT minus G by RT. Those are Ts, G equals H minus Ts, and from that we get S by R equals H by RT minus G by RT. What we will do now is we will stop here with this equation 331, because the further development we would like it to be a little more continuous, and we will continue with this in the next class. See you in the next class.